like these two machines, and we have a VF here. This is the excitation voltage, and we have the stator here. So the stator is open. We don't have anything. The only thing is we are going to measure this current here. Let's put it here, IF. And I'm going to measure this voltage. I'll call it the open circuit. Right? I'm not sure here. Call it phase open circuit or the line there. I think the line they call it the open circuit. Phase, sorry. So I call it phase. Yes. Now, if there is no load, right here, if there is no load, means nothing is connected to the motor. You can talk about electrical, or you can talk about the generator, right? How much electrical loss we have here? Zero. Why? Because there is no current. There is a small, because it's open, right? The circuit is open. There is no current going through here, so we don't have any resistive loss. Now, if the excitation system is open, this is the excitation system, right? If this one is open, how much voltage will be induced in the machine? This one, yeah. Can you tell me how much is going to be? Zero, a little bit more than zero. Why? There is a residual flux, right? If there is no residual flux, yes, because if we go back here, see, again, there is omega here, right? Sorry, there is an IF here, right? If the circuit is open, there is no IF. This one is going to be how much? Zero. By default, there is a little bit of IF built into the core, right? The core is a little bit magnetic, right? So there is a small voltage, a very, very small voltage. Let's assume it's zero for now. So and to do this for this machine, something I forgot. The rotor is rotating with a synchronous speed. We have a prime mover. We rotate the rotor at a synchronous speed, right? But this one is open. This one is open, right? This one is rotating with a synchronous speed, but it's open. So the voltage is going to induce here. It's going to be very, very small voltage. The open circuit is going to be very, very small voltage. But tell me what kind of loss we are going to have in this system. Are we going to have any electrical loss in the system? No. Why? Because the armature circuit is open. And when I talk about the loss, electrical loss, I don't care about the excitation system loss. I talk more about this part, right? So you can see in the circuit, there is nothing about the excitation system to put it here, right? So there is no electrical loss. Do I have any iron loss or core loss? Let's go back to what was the core loss. In the synchronous machine, the core loss was in the stator, right? How much? We have a frequency because the machine is rotating with the synchronous speed, right? It's not the case to say the machine is not rotating, so frequency is zero, so there is no core loss. But how much flux we have? How much flux we have? You remember the core loss was the hysteresis plus eddy current, right? There were two parameters. One was the frequency, one was the DM, right? Maximum flux density, right? Those two, if either of them was zero, so the loss is going to be zero, right? In this case, frequency is not zero because the machine is rotating with the synchronous speed, right? But how about the DM? How much DM do you have? The residual, right? Yeah, because this one is open, right? We said the only flux we have in the circuit is the residual. Residual is a very, very small value. We can assume that one is almost zero. So basically, there is no core loss. There is no resistive loss. There is no core loss. And still, to rotate this machine, we need some power, right? We need to put some power to rotate. What that one goes? What kind of power is that? Mechanical loss, right? Like a friction, like a windage loss. Because as soon as the machine starts to rotate, there is some kind of wind going through the machine, right? So there is a mechanical loss. If the excitation system is open and we measure the power, you know what I'm saying? We measure how much power. We have a shaft here, so if we connect this one to a prime mover and we are rotating it, so I put 100 watt in, right? I need to have a motor here to rotate this machine, this rotor, right? Basically connected to the another prime mover, right? And that prime mover is going to run this one to, these are coupled together, right? Coupled together, right? So you see this machine needs like 100 watt to rotate at synchronous speed. Basically this one is the power loss of this one and this one together, because this one also has some power loss, right? But let's say this is the ideal. So this test, the P open circuit in this case, is going to give us what? POC when IF is 0 is going to be P net loss, right? P mechanical loss. It's going to give us that one. Now, we measured this one. We measured the mechanical loss of the machine at the synchronous speed. You know, mechanical loss depends on the speed, right? But because this machine is a synchronous speed, at any load, it's going to rotate with synchronous speed. We need only that, right? Now, let's close this one. Close this switch. And I'm going to plot two curves here. Let's say VOC versus IF. And P core versus IF. Right? So if here is open, how much is the VOC? Is the EAF, right? So basically here I can change it to EAF, right? It's the same VOC, I say EAF. Like a no load curve for the DC machine. Remember we said we measure the E when the machine is open, we change the excitation current, we rotate the machine at synchronous speed, and we measure the V open circuit, and that one is going to be EAF because there is no current, there is no load, right? V terminal and EAF, they are the same, right? Now here, going forward, how about this one? Can I say, look at here, so speed is fixed, right? It's a synchronous speed, right? And the impedance, the inductance is fixed also, right? So basically, this is the RMS value of EAF somehow, right? With some coefficient, right? Instead of say IF, I can say EAF, right? Or instead of EAF, I can say V open circuit, right? So basically, that axis could be VOC which is the EAF, right? I say IF, which is proportional to this one, right? Right? Or it will be other things. These two are proportional to. Right. Now let's look at it. Initially, it's going to be like this. Okay, let's assume there is no residual flux and there is no saturation. What we are going to do, we are going to increase this current. We have a big resistor here. Initially was 0 if there is no residual, right? Ideal case. The voltage is going to be 0, right? So I'm going to start to close this switch. We're going to have some current, right? So as soon as I have a current, I'm going to generate what? I'm going to generate some back EMF, right? You can see over there. So basically, if I increase my IF, I start to reduce this RX value, right? Call it RFX in full field. When I reduce this RFX, what is going to happen? The current is going to go up, the current is going to go up, current is going to go up. And look at here, this voltage is going to get bigger, 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 right? Constant number, this is synchronous speed. Constant inductance, right? So basically, it's going to be linear with IF, right? So it's going to be like this. We call this one air gap line, I believe. Yeah. This is the voltage will be induced if everything is ideal and there is no saturation and there is no residual, right? What is going to happen in reality? First of all, we are not going to start from 0, right? We are going to start from a little bit above 0. For example here, right? This is kind of exaggerated, but just I want to show you different, right? We're going to start more than 0 because there is some residual flux, right? So what is going to happen up to some point is going to be like this. But what is going to happen? It's going to saturate. Wow. What happens to that equation? Can you tell me? Omega is fixed. IF is increasing. LAF is fixed. But what? So what is going to start to get? Huh? No. Which thing? This one? Forget it. Just look at this part. I want to sign theta, right? Over there. What is going to happen? Why I'm bending that way? So what increase what?
I actually used to point saturation.
What increase what? No, I can increase that. I will show you.
EAF.
Oh, yeah. No, I can increase that.
Is the EAF capped by the no load volt?
No. Why that one is not to bend? Can you tell me why? This one is not fixed. I said fixed, but it's not fixed, right? That's it. It's fixed up to some level, right? And before saturation, when you get saturated, this one is not gonna start to reduce, right? When you get to, you're right, you get to saturation. You know, when you increase the IF, yes, the core is gonna start to saturate. When the core starts to saturate, go look at the equation we had for the inductance. You know, look at here. For example, one example we had was like this, right? We have a mu1 here, and here we have a mu2, right? Right? It says L is equal to n squared over r, right? How much was r? R was L over mu a, right? So basically, it's going to be mu a n squared over L, right? We cannot change L, we cannot change N, we cannot change A. These are fixed. These are the physical dimension of the machine and number of turns, right? Well, look at here. When we are in the linear part, right? Mu1 is more than when we get to the saturation part, right? So mu is going to start to reduce. If the mu start to reduce, L is going to start to reduce. Here we said, let us assume there is no saturation, nothing. L is fixed, right? If there is no saturation, L is not going to change. But if there is a reality, you know, after some point, the core starts to saturate. Basically, this L value is going to start to reduce, right? It's not going to be fixed. For some portion of this curve, it's going to be fixed, right? This is the linear part. But after some point, we're going to get to saturation, so L value is going to change. So that's the reason this curve will start to bend, right? I'm not sure what they call this one. We call it OCC. We call it open circuit characteristic, OCC. There's an air gap line. Air gap line is good if we know for sure the machine is not going to get saturated, right? If the machine is not getting saturated, we can use the air gap line. If the machine somehow is designed to get to that saturation point, we have to use the OCC for the future calculation. Now let's look at this one. P-core. P-core is going to be like something like this. P-core, yeah. It's going to be something like this. Can you tell me why? That's like a quadrant, almost. Almost quadrant. Can you tell me why? Frequency is fixed. Machine is rotating at synchronous speed. We're not changing.
Because as IF is increasing, so is VOC, and you were saying it's increasing proportional. The EAF is increasing proportional IF,
so what's the relation with the EAF with the core loss? What do you want to say? What's it? No, I know your name now.
I had an idea, but it's wrong.
You can say, don't worry, it's wrong.
Well, I was going to say I squared R, but obviously it's not.
No, R is the resistance. We're talking about core loss.
Is it because EAF is proportional to the phi?
That's exactly, you know, because EAF is proportional to phi, right? and the core loss and was the hysteresis loss and the eddy current loss. They were proportional to B or phi, right? A square. There was a square, if you remember, for B a square, and one of them was 1.6, something like that. If you go back to look at, so that's the reason. Basically, B is kind of representing flux, right? And core loss, hysteresis, and eddy current loss, they're almost proportional to Bm square, right? So basically, we see something like this. This is the core loss for the machine. Now, so what you do, you increase this one to finally see the nominal rated voltage here. For example, they say this synchronous machine is a 480 volt, right? 480 volt is the line to line. I don't know, 480 divided by square root of 3 is 277, right? So basically, you would take a machine with synchronous speed, you increase the IF, finally you see the rated voltage here, which is 277. You stop them, usually don't go there, or you can go 10% more than that, but don't go far further than that because you can kill the machine, you know? Because the machine has an isolation which is related to the rated voltage of the machine. Now we got to the rated voltage of the machine and synchronous speed. And if you measure the power now, the POC, let's call it here. I call it POC at IF. POC is going to be P mech loss plus P core, right? Plus P core, right? When we have the excitation system. So if you do it with the synchronous speed nominal voltage, you have these two, right? Together. You measure these two together. If you want to separate these two to see how much is this one, how much is this one, what should I do? I'm going to open the excitation system, right? If I open the excitation system, this one is gone, right? So I'm measuring in it. You can separate the mechanical loss and the core loss. And by the way, we call this one constant power loss, because when you are at the rated voltage, you know, when you are at the rated voltage, P core is a hysteresis and eddy current. Machine is rotating at synchronous speed. The voltage is fixed. The frequency is fixed, right? For example, this is the rated voltage. For example, Vn. So you have some values here, right? So basically, if the speed is fixed, this is going to be fixed. This is synchronous speed. This is not like an induction machine to say the speed is going to change. Or there also the speed is not going to change very much, but a little bit is going to change based on how much is the flick. Frequency is fixed, and if you are at the rated voltage, so basically core loss also is going to be fixed, right? With the different loads, core loss still is going to be fixed. You are at the rated voltage, you are at the rated frequency, so the core loss will be fixed, mechanical loss will be fixed. They call this one T constant. This is a constant power. But if you want still to separate them, how much is the core loss, how much is the mechanical loss, you can open the excitation system and measure the loss. This one is going to be the mechanical portion of that. This is because of friction, windage loss, and those kind of. You can measure them separately, you know. Now we did the open circuit test. The next one is the short circuit test. I'm going to use this one. Keep this one in mind. But let's go to the short circuit. So what was the test condition? Machine is rotating. This is very important. Machine is rotating at synchronous speed, and we are increasing IF from 0 to some value, which we are going to generate the rated voltage, Vn here, right? We are going to go there. You can go a little bit more if you want, but not more than 10%, 5%. You keep it there. Now we are going to go to short circuit test. We call it SC. This one is the short circuit test. This is the OC, open circuit. Let's draw the circuit. We are going to have